So, hello everyone. Today we are going to start the third lecture of module 3, that is enzyme kinetics. So, today we will be discussing the evaluation of kinetic parameters. So, if you remember in the last lecture we discussed about the enzyme kinetics, particularly the rate equation, and from the rate equation how we derive this kinetics equation following two approaches. The first one was rapid equilibrium approach and second was quasi steady state approach. So, in case of rapid equilibrium, the Km was defined as K minus 1 upon K1, and in case of quasi steady state, Km was defined as K minus 1 plus K2 upon K1, and in both the cases the rate is defined as V as V max S upon Km plus S, and the equation for the same is E plus S. This is a reversible step, K minus 1 K1 forward reaction rate K1 backward reaction rate K minus 1. This is leading to enzyme substrate complex, the rate constant K2, that is also known as catalytic constant E plus P. Now, following further, now it's once we know this kinetic equations, now it's important to evaluate the kinetic parameters. So, before going for the kinetic parameters, first we will see how the rate of enzymatic reaction is defined in terms of activity and unit. So, as we know, what is the rate? Rate is dP upon dt, rate of product formation per unit time, or rate of substrate utilization, change in the substrate utilization per unit time, and this is a depletion. So, we put minus sign here. Now, the rate can be defined in terms of enzymatic activity. So, enzyme activity says moles of substrate converted to product per unit time, and that is exactly the rate. So, rate at which an enzyme catalyzes a biochemical reaction is called the enzyme activity, and enzyme unit is the measure of enzyme activity. So, it says the amount of enzyme that catalyzes the conversion of 1 micromole of substrate per minute under the standard conditions, and this enzyme unit is defined as U, or sometime we write as a international unit. So, basically enzyme unit is a measure of enzyme activity, and enzyme activity is rate. So, one unit of enzyme activity we write U, or international unit, but in SI it is called as CATL, KAT, and this is defined as amount of enzyme required to convert 1 mole of substrate per second. In the enzyme unit, this was 1 micromole of substrate per minute, and in case of cattle it is 1 mole of substrate per second. Now, we can derive relation between cattle and unit. So, this will be 1 mole is 10 to the power 6 micromole, and 1 minute is 60 seconds. So, it becomes to be 6 into 10 to the power 7 unit. So, 1 cattle is 6 into 10 to the power 7 unit. So, we have seen the activity and unit. One more term comes here is the specific activity. So, this specific activity quantifies an enzyme purity and efficiency. For example, if specific activity is higher, means we are having a more purified enzyme preparation. And how it is defined? Specific activity is calculated by dividing the enzyme activity by total protein concentration. Now, this protein concentration can be in the milligram or it can also be in the milliliter. So, when it is in the milligram, the unit of specific activity will be unit per milligram, and when it is ml, the unit of enzyme specific activity will be unit per ml. So, this is very important to remember that rate is related with the activity, enzyme unit is a measure of enzyme activity, and specific activity is the ratio of enzyme activity divided by total amount of protein. Now, we can transform this Michaelis-Menten equation to easily decipher the kinetic parameter from the experimental data. So, we know this is the Michaelis-Menten equation V as V max S upon Km plus S. So, if I write 1 upon V, this becomes Km plus S divided by V max S. We can segregate this part, this becomes Km divided by V max into S plus S divided by V max into S. This cancelled out, so it becomes V Km upon V max into 1 by S plus 1 upon V max is equals 1 upon V. So, in this way, if you know this experimental value, how rate is changing with respect to substrate, then we should be able to calculate this Km and V max. The first one is Line-Beaver work plot. So, it says you are having this equation, you plot 1 upon V and 1 upon S. So, here what will be the slope? Slope will be here Km upon V max and intercept will be 1 upon V max. So, in this way one can calculate the kinetic parameter, but here there is the data point at low substrate concentration influence both the slope and intercept here, because when there is low substrate concentration 1 upon S value becomes much higher. Now, this equation can be further rearranged. So, it says V equals V max S upon Km plus S, and we have written Line-Beaver work plot 1 upon V is Km upon V max S plus 1 upon V max. Now, this ED Hofstee plot, it says you can write V as V max minus Km into V by S. So, it says you can, there is a possibility to further rearrange this equation, and in this case ED Hofstee plot, if you know the rate and you know the substrate concentration V upon S. So, you should be able to plot V, Y, X will be V by S. Here the slope will be minus Km and the intercept will be V max. V max is the intercept, slope is minus Km, because this is, you can see this is a negative slope. Now, it's, you can see the rate is in the both x axis and y axis. So, this, the challenge with this ED Hofstee plot is this subject to a large error, since both axes contain the velocity V value, and this is less bias at low substrate concentration as compared to the Line-Beaver work plot. So, another approach is we had 1 upon V as V max, sorry, Km upon V max S plus 1 upon V max. What you can do? You can multiply with S. It turns out to be S upon V equals Km upon V max plus S upon V max. Now, here you can directly plot S upon V as Y and S as the S upon V. So, here the slope will be 1 upon V max and the intercept will be Km upon V max. So, as the slope is 1 upon V max here, this plot is used to determine V max more accurately. So, these are the three way, this Line-Beaver-Burke plot, that is the most common one, followed by the E.D. Hofstee plot and then Hens-Wolf plot. So, E.D. Hofstee plots, y axis is the V, x axis is the V upon S, and here y axis is S upon V and x axis is the S. So, this is the summary. You can see Michaelis-Menten equation is V as V max S upon Km plus S. Line-Beaver-Burke plot, it says 1 upon V, this is the y axis, y, this is x, this is slope and this is intercept. Hens-Wolf plot, this is the y axis, this is the x axis. So, this is the slope and this is intercept, and E.D. Hofstee plot, this is the y axis and this is the x axis. Km is the slope and V max is the intercept, and this slope is a negative slope. One option is one should be able, as we know, V is minus ds upon dt. So, we should be able to also get the analytical solution for this. So, if I write this minus ds upon dt is V max S upon Km plus S, I can rearrange this minus ds upon dt equals Km plus S V max S. You can divide by S here. So, this becomes minus ds upon dt Km upon S plus 1 to V max. So, if we integrate this, so we will end up 1 upon S will be ln S. So, we are having Km into ln S naught upon S, integration of 1 will be S. If we apply the boundary condition S naught to S, it will be S naught minus S, and V max integration of dt will be T, V max into T. So, in this way, if we know the value of what was the initial substrate concentration, it is the final substrate concentration, how much time it required to utilize this substrate from this to this, we should be able to calculate the kinetic parameter Km and V max here. It can be either way also. If Km and V max are given, we should be able to calculate the value of how much time it requires to utilize the substrate from S naught to S. Now, we will see a few examples based on this concept. It said protein concentration of a crude enzyme preparation was 10 mg per ml, and from this 10 microliter of the sample gave activity of, what is the activity given? 5 micromole per minute. If you remember what is the unit of enzyme, it says micromole per minute. So, it becomes 5 unit activity is given. What you have to calculate? The specific activity. To calculate the specific activity, we need to know the mass of protein. What was the concentration? 10 mg per ml, and how much volume was taken? 10 microliter. this is a 10 microliter, you can convert into the milliliter, right. So, this will become mass of protein is 0.1 mg, right. Alright. So, now the answer will be specific activity unit per mg. Now, it is interesting to see this specific activity defines our enzyme's purity and efficiency. Now, for the same activity, if I say I added 20 microliter, I added 20 microliter of the enzyme, then what will be the mass of enzyme? Mass of enzyme will be 10 into 20 into 10 to the power minus 3 equals 0.2 milligram. So, it says 0.2 milligram means more amount of enzyme is required for the same activity. So, here if I calculate the specific activity, then this becomes 5 divided by 0.2 equals 25 unit per mg. So, I put the both 10 microliter and 20 microliter. So, if you require more enzyme for the same activity, it means where the specific activity is higher 50, that enzyme has better activity as compared to the where the specific activity is the lesser or 25. Now, here we can see one more example. It says given Michaelis-Menten kinetics, a concentration of enzyme E, assume Km value of 6.2 millimole per ml. Initial and final substrate concentration were 14 and 0.2 millimole per ml, and given is the maximum rate of for the enzyme is V max 5.6 micromole per ml per minute. Determine the batch reaction time. So, we have to calculate the value of T. So, what it says, if you just remember, this can be solved analytically. So, it says Km ln S naught upon S plus S naught minus S equals V max into T. S naught is 14 millimole per ml, S is 0.2 millimole per ml, V max 5.6 micromole. So, we can write in millimole 5.6 into 10 to the power minus 3 millimole per ml into minute, and Km is 6.2 millimole per ml. We just see Km is known, S naught upon S is known, V max is known. We can find the value of T. If we calculate, we will get the value of T as 7168 minute or 119 hour. So, we can take one more example here. So, it says following data has been obtained for two different initial enzyme concentrations. So, in one case E naught was 0.015 gram per liter, in other case it was 0.00875 gram per liter, and this is the value of rate, and this is the value of rate for the in one case of enzyme, and this is the other case of enzyme, and these are the substrate concentrations. So, these are the experimental data. Now, what you have to find? You have to find the value of Km, you have to find the value of V max for both the enzyme concentration and also the value of K2. So, as here S is given and V is given. So, it is easy for us to go for ED Hofstadter plot V and V upon S. So, what you have to do? Other option may be we can go with Hans-Wolf plot, which says S upon V and S, because S is given, V is given. So, we can get S upon V and S. So, here we are discussing S is there, we can calculate the S upon V from the given experimental data for both the enzyme 0.015 and 00875. So, this is the value of S, S upon V and S upon V. Now, we can plot the value of S upon V versus S, that is the Hans-Wolf plot. So, if I plot this, then slope will be 1 upon Vm. So, this is accurately used to calculate the Vmax value, and intercept will be Km upon Vmax. So, here is the plot given for both the cases. So, you just see the slope is 0.6 here, slope is 1 in here, and Km upon Vm is 5.5, Km upon Vm is 10. Now, from the slope we can find 1 upon Vmax. So, here what will be the value of Vmax? This will be 1 upon 0.6, they will get 1.7 gram per liter per minute, and here what will be the Vmax? 1 upon 1. The second case, the Vmax will be 1 gram per liter per minute. Now, Vm upon Km upon Vm is 0.5, Vm is already known. So, Km will be Km upon Vm is let us say 5.5, Vm already 1.7, so Km will be 5.5 into 1.7, that will be 9.35 gram per liter. So, we got the value of Km. Similarly, from the slope here is the 10, we multiply 10 here, so we got 10 gram per liter Km. Now, next comes to find the value of K2. How we are going to find the value of K2 here? K2. So, for K2 the equation is very simple, it says Vmax is K2 into E naught. So, we have two different E naught value, Vmax we have already calculated. So, you apply this equation. So, it says K2 equals Vmax upon E naught. So, Vmax was 1 upon 7 divided by 0.015. So, it will be 1110 gram per gram enzyme per minute. Here it will be 1 divided by 0.00875, this will be 114 gram per gram enzyme per minute. So, here we discuss this how to calculate these kinetic parameters from analytically as well as the by doing the double reciprocal of Michaelis-Menten equation. So, we discuss this Lineweaver-Burke plot, ED Hofstadter plot and Hans-Wolf plot. So, I will stop here. Thank you so much.